Well, welcome back, everyone. Looks like we can get started. We have several people in Zoom today, so whether you showed up in Zoom in person, or maybe you're going to watch the video later, I'm glad that you made it in one way, shape, or form. Welcome back, folks. Well, we're getting through the course content. It's been a pretty tough semester. One thing that's made it tough for me is this is the latest class I've ever taught, and ending at 8:40 really kind of gets taxing once you get to that very end spot. But we're just nearly done with this week. And next week, we're going to be finishing off section 15.4 and then transitioning into reviewing for the final exam. Well, there's lots of things jotted down with the methods that we've been discussing so far. The big takeaway so far is our second to last section, 15.3, is very similar to the final section, 15.4. The only difference is what your parameter is, what your data type happens to be. We're looking into categorical data with two outcomes. So the moment you determine it's categorical, the parameter is P, and the test proceeds in this way. The test statistic takes on a particular form involving a standard deviation. We'll look into a couple more examples walking through these formulas. But if the data happens to be quantitative, it just means there's a new parameter, mu, the population's mean or the population's average. The null alternative hypotheses are stated in the same way, just a different parameter. The test statistic, it looks different, but you have to ask yourself, is that really different? Let's look at both of these test statistics at once. On categorical data's test statistic, you take your data, the population's proportion of successes. For quantitative data, you take your data here and calculate the sample mean. Then you go to the hypothesized value in the null hypothesis on both, whether it's a mean or an average called mu naught. And we calculate the distance from the value of your data, p hat, or mu naught, away from the hypothesized value. Then you're just calculating standard deviations. For the categorical data, you're calculating a literal standard deviation that you would get if you assume the null hypothesis is true. But for quantitative data, it's a little bit more finicky. Assuming the null hypothesis is true won't give you the standard deviation. So we use the standard error again. So that's the setup so far. And just for quick reference, here's also the confidence interval methods that we used for both quantitative data and categorical data. So there's lots of parallelism between our methods. And this is possibly a great way to kind of organize your notes. First, determine what the parameter is, what the data type is, and then list out the methods. It's kind of interesting that we can fit it on one page. There's more to the story, but this is the full set of the main formulas. So we'll finish off section 15.3 with a couple more examples, and then see how it goes in 15.4 for the quantitative data. Well, endless questions or comments at all, folks, before we jump in? Okay, well, in case you want to come back to this, the stuff usually just disappears the moment we get going into the notes. But if you want a place to come back to this as a one-stop shop for all the formulas, let's paste it right here on the actual lecture notes for the day. Okay, so you can come back to this as needed if you prefer. Now below is the full readout of the hypothesis test for sample proportion. We check the conditions for a random sample or a representative sample. We ensure the number of expected successes, expected when the null hypothesis is true, and failures both exceed 10. Then that's the test statistic with standard deviation we were observing. The tricky thing about hypothesis test after computing your test statistic Z is you have to decide what test you're running. If it's a right-tailed test or a two-tailed test, this is the one that we did last class, or a left-tailed test, the methods are slightly different. If you can draw the sketch, and then just remember on the two-tailed test, you're doubling an area, then you're always going to be on the right track. So we're going to emphasize that as we get through our next problem. So this is the refresher on the methods. Any questions at all, folks, before we jump into our next problem? Okay, so here's where we left off on the end of Wednesday. We started this problem. We did kind of the heavy lifting of this problem of breaking down the context really meticulously if you follow all these arrows everywhere. Then we wrote down what the parameter P was. P is the population proportion of people who indicated they sent a text message while driving among all 16 to 17-year-old drivers. So it seems like kind of an ageist study. We're looking into new drivers, really, by the sound of it. And the question of the problem was, does these data provide convincing evidence that more than, so it was a right tail test, a quarter, that was the tricky part. A quarter is 25%. And so the hypothesized value is a 0.25 in decimal form. So more than 25% or 0.25 Americans in that age range have sent a text message while driving. So that's why we formed the hypothesis. The null is that no, it's not more than a quarter. There's nothing different from a quarter. It's about 0.25. But the alternative hypothesis is testing directly. Yes, it is more than a quarter. P is greater than 0.25. We're testing at a significance level of 0.01. So just as a reminder, we also wrote it in here at alpha equals 0.01. So if the p-value for the test is less than that 0.01, we have evidence that the alternative hypothesis, HA, is true, which is really the whole question of the problem. If there's a question mark, oftentimes that conveys the hypothesis test, alternative hypothesis. So this is just the statement in words, and that's it in symbols down below. Well, any questions at all, folks, with just the warm up on the context, the refresher? Okay, first thing we'll do to start this off is look into conditions. Part one of the conditions is we're hoping that it's a random sample. If they achieved a simple random sample, that would be fantastic and amazing. They might have used census data or state data to make that happen. But what if they tell us to determine randomization? Say, go to where it talks about the sample. We had a sample size of 283 drivers in that age range, and we're just told it's representative of American teens, of every person. We're assuming that they're a driver, age 16 to 17 in the United States of America. So that's pretty vague. If we trust them, then we can go ahead and run the whole test. So let's just say here, at least we met one portion of the conditions, but it leaves a lot to be desired. We'd want to definitely, if we're concerned about this data, consult with the Pew Internet and American Life Project to see exactly how they got that, and we can judge for ourselves how representative it might have been. So let's say here, the sample is stated to be representative and so the condition is met. Hello, I was just telling the class we have kind of a larger Zoom presence, so glad that you're here to kind of balance it out in the in-person section. We're starting off the very first problem of going through the teens and distracted drivers. And really, we just kind of refresh the context, and now we're checking into the conditions. Any questions at the moment, folks, with the representative sample?
On the account that I was late, we had finished all the way up through A, right, last time?
Yeah, we finished A entirely. Yeah, we set up the parameter, proportion of people who indicated, that's special language there, they admitted to essentially, they sent a text while driving among all 16 to 17-year-olds, and this is national data, so in the USA. The null is that P is 0.25, and we're doing the right tail test, that the proportion is greater than 0.25, more than 25% indicated they've sent a text while driving. Other questions at the moment? Okay, let's move on to the next part. So whether it's addressing randomization, independence, these are a lot of things that are hard to really assess, but determining if the sample size is large enough, part two, that's not so bad. That's pretty objective and direct. The first thing we do is look into the number of successes and failures, not in the sample. The fact that there's 74 successes is totally irrelevant to us, which is interesting. What we do is we assume that that null hypothesis right here is true and count the expected successes we should see in a sample size of 283. So let's say it this way, just as a strong reminder. Number of successes when H naught, P equals 0.25 is true. And we'll count the number of failures when H naught, P equals 0.25 is true. Notice we're making this assumption pretty much everywhere when we run this hypothesis test. We mentioned way back in section 15.1, already feels like a long time ago, the very first step in hypothesis testing, no matter what the data type is, quantitative or categorical, is you assume that null hypothesis is true, no matter what it is. So we've made those assumptions. The sample size is 283. So if we assume that the sample size or the null hypothesis is true, the number of successes we expect is n times p naught, which is 235 times 0.25, which makes sense. It just says we expect 25% of the sample to indicate they've texted while driving. If the null hypothesis that 25% of the nation indicates that is actually true. So now we're back to the calculator, 235 times 0.25 absolutely meets the benchmark. This had to be greater than or equal to 10, and we get 58.75, which is greater than or equal to 10. So we have enough successes. That means we have enough failures, but we have to say what this number is. Oh, Coral says, do you mean 283? Thanks for spotting that. Yeah, that should have been a 283. Not sure where a 235 came out. It just seemed right. I wrote the error there and duplicated it. Let's fix that right away. So 283, that's going to change the value here. And then back in the calculator, 283. That gives us a 70.75. The condition's met either way, but that's a pretty important correction because you can imagine if you're doing this problem in MyLab statistics, they're going to notice if we get the wrong value here. So we could essentially lose that part of the question entirely without getting that right. So with that correction, we'll get this part right as well. You can take n times 1 minus p naught, or you can just take n minus 70.75. That's the number of expected successes right here. So subtract from the sample size, and you get the number of expected failures. So 283 minus 70.75 gives us 212.25. Also definitely greater than or equal to 10. So on both sides, we meet the requirement. The sample 283 was large enough. It might seem like it's a no-brainer, it's large enough. That's a huge study, 283 participants. But that just depends on the null hypothesis. If we're studying maybe not teen and distracted driving, but maybe some rare genetic condition, something that's extremely rare in the population, and your null hypothesis happened to be 0.005, or maybe even smaller, this sample might not have been large enough. So it just depends on what you're testing, what the null hypothesis actually is, to determine if your sample size was large enough in the very first place. But here, condition 2 is met. We can say both are larger than 10. The sample size is large enough. So now we're done with the conditions. Next thing we'll look into is the mechanics, computing the test statistic, the p-value, and making our conclusion. Well, any last questions at all, folks, with looking into the condition checking?
Are those the only two conditions that you're looking for, if it's representative of the population? Because on the last one, didn't we check two if it was random?
Yeah, so we had a different situation on that one. This one said the study did not randomly select the participants. Let's see here. Did randomly select the participants. We were just told straight out that it was a random sample. 1283 randomly selected 18 to 25-year-olds. So we just said that on condition 1. Then condition 2, that was the only condition we also checked on this one, was just to see if the sample size was large enough as well. And MyLab statistics, it also is going to ask if the data is independent or not. That's usually just an easy pass. The data is almost essentially always independent. You need to know very special information if it was dependent.
They also ask if it's a one proportion test.
Oh yeah, it's asking what test we're using. Here in these entire section notes, 15.3, it's always going to be the one proportion z-test in each and every case. Now that's one of the weird things that I wish I could delete it out of MyLab statistics, because really this is the only test we know about. So it's automatically going to be the z-test for one proportion on every single one of those problems.
So I guess to ask a better question, your number 1,
Yeah,
in this case where it says, if we're answering if it's random or if it's representative, is that the same?
yeah, that's tying back to the same condition. It comes from right over here in the notes. Part 1 is whether we have a random sample, and here's the or part,
Okay,
that it's at least representative.
perfect. So that's what you're looking for, one of those two things.
Yeah, exactly, for condition 1.
Perfect. Thank you.
Yeah, absolutely. And to talk about MyLab statistics again, I think another condition they ask is they'll ask you to assess if the population, or excuse me, if the sample size is not more than 10% of the population size. So that's another possible question there too. But for the notes, I felt like focusing on just these two things was a good 2 things we can check directly and have some laser focus on. Other questions at the moment? Okay, thanks for asking about those. Now, going back to part C, calculate the test statistic. You know, this one's kind of tricky in a certain sense. To calculate the test statistic, you need to know the statistic, first of all. So let's carry this down. P hat is 74 divided by 283. P hat is 74 divided by 283. Hardest part about this is maybe not just the formulas, but also the rounding. Rounding for categorical data can be finicky because of strange things that can happen in the denominators. So if it says to round to 4 decimal places, best practice is to keep 5 or 6 decimal places. So let's take 74, divide by 283. Let's go for accuracy. I'll keep 6 decimal places on this. 0.26148. I guess that's 5 places. 484. Let me double check my numbers. 0.261484. So we've got p hat down. Now that you have p hat, it's a good time to go and just write down the formula for the test statistic. So the test statistic itself, indicated by a z. it's going to be p hat minus hypothesized value p naught. So we're going to use that 0.25 again. Divide by the exact standard deviation of the statistic p hat when the null hypothesis is true. So now that we have the formula down, we already have p in hat. P naught is the hypothesized value already way up here in the null hypothesis, duplicated in several other places as well. The next thing to calculate really is the standard deviation of p hat. That's a pretty big formula in its own right. Standard deviation of p hat, it looks familiar. It goes p naught times 1 minus p naught divide by sample size n. So when we plug that in, we go back to the null hypothesis. Here's our p naught value. Compute square root of 0.25. 1 minus 0.25. I guess you could have put 0.75 there directly, but just to show how the formula flows, that's what it would look like. N is the 283. And right, calling it SD is just fine, but let me keep some parallelism on the symbols. It's standard deviation of p hat. It's not saying multiply by p hat, it's just one whole symbol to describe the standard deviation. So now we're ready to toss this into a calculator. This was not too bad to compute. Go second square root 0.25 times 1 minus 0.25 divide by 283. And here's what we get. 0.0257399. So that's 1, 2, 3, 4, 5, 6. This is another round with carry kind of problem. So 0.025740 is what I would get accurate to 6 decimal places. Well, once we put all this together, we now have the test statistic z, and that will inform us what the p-value is for the test. So a lot of bouncing around. First thing we wrote down was p hat. Then we have the formula down for z. We computed the denominator. So now go back to z and just dump everything into that formula. First, it's p hat, cited over here, 0.261484, minus the value for p naught. That's the 0.25 that we've been putting down on paper in lots of different places. Divide by standard deviation, 0.025740. So we're just about there. One more calculator computation, 0.261484 minus 0.25 divide by 0.025740. Let me know if you get slightly different values. I'm getting a p-value, a test statistic z of 0.4462. Now rounding this one to 4 decimal places. Okay, I think we've got it. Any last questions at all, folks? Getting the test statistic down? Okay, once you've got the test statistic, you're about nearly there. In fact, we can make a prediction on what we're going to make as our conclusion already. This tells us a number of standard deviations. And what it's telling us is the distance from our data, the sample's proportion of successes, and the hypothesized value that percent of drivers is 25%, that distance is less than 1 standard deviation. We're almost assuredly not going to reject the null hypothesis. But we still have to get the p-value down to see how close we got to rejecting. And so that's where it's going to depend on what is the test we're running in the very first place. Right here, where we put a greater than on the alternative hypothesis, it told us we were doing a right tail test. So that means we get the p-value in a very specific way. We drop the test statistic z wherever it is under the normal curve, n01, but we are going to shade to the right to match the right tail test. That's kind of satisfying in a way. There's parallelism here. If you use the greater than sign, you're thinking right-tailed, which means shade to the right. So it's kind of capsulated right here. Let's put the whole thing on the notes just for another quick reminder on how we get this p-value out. Kind of makes the notes a little bit longer, but it's kind of nice to cite right in the problem why we're doing about what we're about to do. So for our specific data, draw just your handy dandy normal curve. It's N01 every single time we run this. And this is because of this shifting and scaling section that wasn't our favorite, is the one after the z-score formula. The mean wasn't really zero, but when you subtracted the hypothesized mean, you've shifted the mean to a zero. The standard deviation wasn't one, we know it, it's 0.25740. But when you divide by a standard deviation, you've rescaled the standard deviation back to a one. So that's why it's N01 every single time you do a test statistic. So we can place zero here. Z is not too far away, so one standard deviation is there. Z is about here. 0.4462. We're shading to the right. Might as well use the same color. And Z kind of tells us what we're using. If you say Z, it means we're using normal CDF. If it was a T test statistic, we would be using T CDF. That'll be in the next section, chapter 14, or section 15.4 rather. So this will be input 1, lower, because we've shaded to the right. Input 2, upper, is 10 to the power 99. I really were just following this as a guide. Right tail test just means shade to the right, and it's a section 5.5 problem. So hit second key vars to pull up your distributions. We're in normal CDF. Test statistic is the lower value, so 0.4462. Upper value we have set right, 10 power 99. So all we had to change, because everything was already set up, is just that one value. When we did this with the two-tail test, we were really, really careful when we got to this line and got the p-value. We had to literally double that. But if it's a right tail test or a left tail test, what you see is exactly what you get for the p-value. So we're done at this stage. To 4 decimal places, the p-value is this. It's 0.3277. That's a large p-value. It tells us the probability of getting data as extreme as this, 26%, indicating that they've sent a text, or more extreme, under the assumption that the actual true percent is 25% for the population. That can happen almost 1 out of 3 times you run the study. It's almost a 33% chance. That's typical, that's routine. That's saying our data getting this value, it's consistent with the assumption of the null hypothesis. It's not too different from what the null hypothesis said. But that doesn't mean we show the null hypothesis is true. We've been assuming it's true from the very beginning. We assumed it's true to compute number of successes. We assumed it's true to get the standard deviation. Our decision here is really very tricky. We are in this situation this time. The p-value is greater than or equal to alpha. We will fail to reject the null, which means we have to write a conclusion that reads, we failed to find significant statistical evidence that this alternative hypothesis, more than 25%, is actually true. It may be true, but we couldn't detect it with our study. We have no evidence in that direction. It almost doesn't matter what the alpha level was, because the biggest this could have been is 0.10. But let's put this back down on our paper as well on context, because again, this is tricky stuff to keep in mind. There's lots of moving parts to hypothesis testing, and this is one of the big ones. So once we get a p-value, when we're about to give a conclusion, let me just find the right spot to scroll into. I'll just bump this up a little bit. Right before we give a practical conclusion, we compare the p-value against the significance level alpha. It was set to 0.01. And we could say in our problem, the p-value, which is 0.3277, is absolutely bigger than 0.01, which is equal to alpha. And so this means the decision in the problem is to fail to reject H naught. So in other words, we're in this case right here. So the answer to part D is just the p-value, 0.3277. Let's box that out to really emphasize it. And the answer to part E is not fail to reject H naught. We have to write that out using the context of the problem in a practical way, just much like with confidence intervals. So here's where we'll pull down what we said our parameter actually was and give that practical conclusion. Any questions at the moment, folks, on just making the right decision, the first row versus the second? Okay, at this part of the problem, here's where our eyes want to go to next. You might have been able to fit this all on paper, but I have to scroll a bit to find this. Go right back to part A. This is the most pivotal portion of the whole problem. It tells you what you're even trying to establish with these data in the very first place. You scroll to about here. And it also tells you how you're going to write out the conclusion as well. So when it says give the practical conclusion, here's what it's going to look like. We don't accept the null hypothesis as true. Just like in a court of law, a verdict of not guilty did not prove innocence whatsoever. And same idea here. We're still going to focus on HA, but we're just going to say we didn't have evidence in favor of it. So borrowing this language, we might say the study failed to find or provide, however you'd like to say it. I'll say failed to find significant statistical evidence. And let's mention our significance level alpha. It wasn't totally relevant in this because once you get that large of a p-value, once again, for any appropriate alpha value, it's going to be fail to reject. We'll still mention it. This was our benchmark for evidence. This was at the 1% significance level. So we failed to find significant statistical evidence at that benchmark for evidence, 1%, that this is true, HA. So we say what P is. So we'll say that the population proportion of people who indicated they sent a text while driving among all 17 to 18-year-old drivers. Takes a moment to say, but we got it down finally. This was a right tail test, so we had a greater than. My computer's working really hard. I'm not sure if you can hear that in Zoom. Yeah, it's trying to lift off. Is greater than. we can say 0.25 because we mentioned proportion. And right there, that's where the problem ends. So no matter what the conclusion looks like, we are always focusing on the alternative hypothesis. We always come back to this one. This is the main question of the whole problem, the research question. So we either address our conclusion by saying we have evidence it's true, or in this case, we failed to find the evidence that it's true in our sample data. So I'll leave these screenshots here just as a reminder of how we got to this conclusion. Let's put another border just to convey once more. The conclusion ends just right here, and this is just the supporting material that got us there. Well, we did it, folks. That's our second top to bottom, nose to tail hypothesis test. Takes a lot of work. There's lots of moving parts. That's why we're kind of going through it carefully and slowly. That's why we're doing so many. We're going to do really our fourth one on these notes, our third full one after seeing the formulas. But any last questions or comments after getting to the end on this one?
There's a question on my lab statistics where the p-value is 0.
Yeah, that can absolutely happen. I think I have one in section 15.4 where that's going to come up. If you ever get a p-value of 0, that means you're always going to have a less than right here, and you're always going to have significant statistical evidence. But let me show you what it might look like in your calculator, though. We'll have one again coming up in the next section notes. Unfortunately, not in section 15.3. But to get a p-value of 0, here's what it would look like. Let's go back to normal CDF. And let's imagine maybe the standard deviation was different. Maybe the sample size was 28,300. That would drop this to something that's kind of close to 0. And now any small difference from the null hypothesis is probably going to be picked up if our standard deviation is so small because the sample is so large. So when that happens, Z becomes huge. It could have been, say, 15.4462. That's plausible. That could happen. And like you're mentioning, I believe this happens in the homework for this section. It could happen in the next section as well. So that's a humongous test statistic Z. It's like saying your sample data is 15 standard deviations away from the statement in the null hypothesis. That's so many standard deviations, but the calculator is actually going to run into a problem on this. You might see something that looks like that.
Now, my next question. But are you ever going to see one, the number with an E after it?
Yeah, we will. So that's something we're going to see in section 15.4. What this is essentially telling us is, let's put this down here just as a great question or great comment to put on the notes. A great question to ask. If you get this value, and it can absolutely come up, we'll see one in our own notes. This means the p-value is equal to 4.2098 times 10 to the power of negative 54, which in terms of moving decimals around, it means that decimal point has to move 54 spots to the left of the 4 value. It's hard to even write that down on paper. That means your p-value is 0.0000 rounded to 4 decimal places, which is a typical ask for these problems. So if it's something outrageous like this, if it's giving you scientific notation at all, that's what the E is really saying. E is a base 10, and then they give you the exponent, negative 54. But in either case, no matter what your alpha level is, 0.01, 0.001 is kind of rare, but even in that case, this is going to be less than alpha, so we will reject H naught. In that case, it's almost guaranteed whenever you get scientific notation. Does that make sense on when that can come up? I think it can get even worse. Let's try another one. Let's go back to normal CDF, and let's just imagine it's something like 500. That would be kind of unusual to get 500 standard deviations. That would tell us that the statement of the null hypothesis was so outlandishly weird, or our sample was just unimaginably strange and alien, that the data is 500 standard deviations away from your null hypothesis statement, something you almost never see. But if your calculator had to handle that, it's going to drop a zero because now that's so many standard deviations, it can't even use scientific notation to describe how small that number is. It actually isn't zero, but the calculator is just forced to round in this one kind of outcome. So you could potentially see this as well. If you get zero, it's really rounded to 0.0000 for decimal places, and you're in that same exact outcome as before. Does that make sense for what's going on in those cases? Awesome. So again, I don't think any of my data got too weird to give scientific notation on these notes, but we'll see it in the next section for sure. Any other last questions, folks, on finalizing this problem? Okay, well, great way to practice this, a great way to really learn it, to get prepared for it is do it again. So here's our next run at it, a whole new example. And this is our last quiz for the entire semester, quiz number 11. Let's take a peek into this one. Quiz number 11 is us doing it again. And then there's several problems to practice as well in MyLab statistics. So here's what quiz 11 looks like.
When's it? Next week?
It's going to be due next week, yeah. And says it's still processing. Let's open it that way. Just click on that. And usually you can open it up. There we go. Canvas is kind of weird with PDFs, it turns out. Here's what the quiz is going to look like. This could have been an example that's in our notes. It's a pretty routine kind of scenario for MyLab statistics. It could be a scenario for the final exam as well. It says a national study found 44% of college students engage in binge drinking. That kind of sounds like a similar scenario. I think we've looked at this before, probably for confidence intervals. But when they say a national study, and then they go on to next to go say a college president was concerned if this is true for their campus. They have a representative sample grouped by class standing of 244 students. That's now telling us that 44% is a hypothesized value. That's a value going into the null hypothesis. 96 successes admitted to binge drinking. And they're asking, is there convincing evidence that the proportion of college students who binge drink on this campus is not the same as the national study, not the same as indicating a two-tailed test. We didn't ask for more than or less than 44%. So you'll run a two-tailed test on the quiz number 11. So practicing these problems will get us in pretty good shape for when we see really just two inference problems on the final exam. There's going to be one confidence interval, either categorical or quantitative. There'll be one hypothesis test, either categorical like 15.3 or quantitative like 15.4. So I'm not going to ask you a whole bunch of these kind of questions. It'll just be two types of questions. One hypothesis test, one confidence interval. So to practice that further, here's our next run through it in the notes.
The confidence interval, is that what we learned at the end of chapter 14?
That's right, yeah.
Okay.
And just to go back to what this looked like, let me see if I can resurrect this. Here's what the formulas look like if we put them all back on the table here. Let me point it to the right thing. There you go. I think it should look about like that. There we go. So when it was a confidence interval, we did p hat plus or minus z star standard error p hat. And for the confidence interval down here for quantitative data, it's going to be y bar plus or minus t star times the standard error. And there's some kind of cool things that happen. With the hypothesis test for quantitative data, 15.4, we do essentially the same sort of thing. And our standard error is going to be the denominator. So we resurrect that from the confidence interval formula. Actually, categorical data is trickier because our test statistic uses a standard deviation, but our confidence interval uses the actual standard error, which involves p hats instead of p naughts. So that's the easiest thing to get mixed up once we have all the formulas on the table. So I put these notes as well in our 15.3 document, so you can scroll up to see it as well if you want to come back to those. But this is essentially all of the formulas for statistical inference that we'll see potentially on the upcoming final exam. We won't use every single formula, just two of them, making sure one's categorical and one's quantitative. Other questions at the moment? Okay, well, let's run through this next problem. So one more hypothesis test with categorical data. And this one's kind of a funny problem in a certain sense. It says, the report, A Crisis in Civic Education, this was done in January 2016, summarizes the data from a survey of another representative sample of 1,000 adult Americans regarding their understanding of US government. So this is really interesting data. I have to admit, government wasn't my favorite class in high school. So if I was in the sample, I might have struggled as well with the question they would have asked. Here's what they did in the study. Only 459 of the adults, so that's a sample size N, let's say N is 459 for the sample size. Only 459 adults in the sample were able to give a correct response to a question asking them to choose the correct definition of the Bill of Rights from a list of 5 possible answers. So I Googled it, the Bill of Rights, just to refresh myself on it. That's the amendments limiting the federal government, granting individual rights to citizens. But it's kind of shocking that if I didn't Google that, I'm not so certain how I would have done on this assessment. And it even seems kind of worse. The sample was, oh, hang on, I think I made a mistake here. I said the sample size was 259 adults, but I should have focused on this part. It was a random sample of 1,000 adults, so that was an error. 459 is the number of successes. N equals 1,000 is the sample. So a success is giving a correct answer on a multiple choice question, which is a low level of understanding for a topic when it's multiple choice. There's only 459 successes, less than 50% of the sample. So number of successes is 459, sample size is 1,000. That means we can calculate p hat as 459 over 1,000, and that's just a 0.459, less than 50%. So this is essentially what they did in the problem. It told us it's categorical, and it told us what the successes are. Now, this one's not a question. There's no question mark here, but it kind of implies a question. It's more of a command. If you see a command statement that could imply a question, that's possibly your alternative hypothesis, the research question or the research command. This is what we're doing in this problem, is encapsulated here. It says, determine if there is convincing evidence that less than half of adult Americans could identify the correct definition of the Bill of Rights. So that's a big statement there. Let's highlight that. That's essentially the alternative hypothesis. This is HA. If it was written as a question, it would have said, is there convincing evidence that less than half of Americans could correctly identify the definition of the Bill of Rights, then question mark. But this one, again, is more of a command. So either way, it's HA, the alternative hypothesis. Notice some of the tricky buzzwords here. It said less than half. Well, that less than half is very specific. Let me just highlight the less than. That tells us we're doing a left tail test. There's going to be a less than in this problem. So this is a less than statement for a left tailed test. But really all that also means is there's going to be a less than sign in the alternative hypothesis. But once we get to the step of the test statistic Z, we will shade to the left to get the p-value. Shade left for p-value. Other part is they told us this is at a 5% significance level. In symbols, this means alpha equals 0.05. We'll compare the p-value against this. We want our p-value to be smaller than a 0.05. And if it is, we'll have evidence that the alternative hypothesis is true. We wrote down a lot of stuff, but there is still one major thing missing. It's the hypothesized value, and it's used everywhere. The null hypothesis, condition checking, the test statistic as well. It's written as P naught. Has anyone seen what it is in this problem? Let's think about this one. Good call, Coral. It's that buzzword right here where they said half. Again, I feel like that's bad final exam writing. I would have said if this is a real final exam question, less than 0.50. I think it's a nicer way to say it. That way we're not wasting time trying to really analyze and x-ray the context, finding this. But saying less than half really means less than 50% or less than 0.50, giving us our P naught value. So that's the major buzzword on this one. Right here. Kind of similar to the last question. Less than half means 50%, which means the value for P naught is going to be, as a decimal number, 0.5 or 0.50 if you prefer. 0.5 would be just fine. So we've got it down. There's the context kind of separated out. The mechanics of the problem, successes, the statistic, significance level is all here. We just have to run through the motions now. Any questions or comments at all, folks, analyzing the context? Okay, so big part of statistics is knowing what we're testing in the first place, knowing what the conclusion is going to look like. And a lot of that mental effort is just right here, saying what the actual parameter is. So here's the step of defining the unknown parameter. P is going to be the population. You could say proportion or percent. We've mentioned that a lot. Let's go for percent this time, just as a variation on the method. It's going to be the population percent. And we can mention the successes failure, or the successes first, or we can mention the population first. Really kind of up to you. We usually always mention the successes first, so let's keep that pattern. A success is a correct response to identifying the correct definition of the Bill of Rights from a list of 5 possible questions. We don't have to write that down verbatim. We can kind of compress this down in the context, make it a little bit more terse. Let's say the population percent of people who correctly identify the definition of the Bill of Rights. I'll skip in a multiple choice test kind of part of the context. We'll let the overall problem carry that portion. But we should mention the population. This is 459 adults. They sampled 1,000 American adults regarding their understanding of the US government. So we can just say among all Americans, taken to mean USA citizens specifically. So that's our parameter P. We have a representative sample from that population. So once again, it's going to really boil down to how they got that representative sample. But the next thing we'll write down is the hypothesis test itself. So this is the part where we're going to state the null and alternative hypothesis. So let's write it down as kind of a sentence. test H naught. The P equals, and I'll leave this blank for a moment, against HA, P and then another blank, at alpha equals 0.05. So this one line is essentially our whole test. We focus on the alternative hypothesis first. We made a big deal that the alternative hypothesis is a left tail test because they are asking us to test in the less than direction. So that's where the less than goes, right there in the alternative hypothesis. Notice we've always put in direct equality each and every time we ran this. And the last thing is to put in the hypothesized value. The value in question is half, or 0.50. I'll write this in as 0.5 since I'm running out of space. So the alternative hypothesis, it should feel like it's just this question or command right here highlighted. We want to find evidence that the percent of people who correctly identify the definition of the Bill of Rights is less than 50%. That seems like the right direction to test if we had only 459 successes. That's 45.9%. But that alone doesn't tell us we have statistical significance. We have to bring in the standard deviation to see really what's going on. First, let's run through the conditions once again. But this is, again, the heavy lifting of the whole problem, part A. It takes some careful looking into the context. That's why I'm only going to ask 2 statistical inference questions on the final exam, because there's a lot of mental effort just on doing this, a lot of thinking time we're putting in. Anything you put down in Scratch is pretty helpful as well. It helps you organize your thoughts. They get the parameter down. And for conditions, I'm only asking 2 quick conditions. We're checking for randomization. Nothing said anything about randomization, so the next best thing, they did make a statement of it being a representative sample. So that allows the condition to pass with kind of a question mark. You might want to, again, alert these people you're curious about their methods to see how they got this sample so you could judge for yourself. We'll say here, the sample is reported to be representative of all USA adults, which is our population. So that condition is met. Next is the success failures condition. Way different with hypothesis testing. We're looking into expected successes, expected failures. So let's write this out again. The number of successes, failures, expected when H naught, P equals the P naught value, 0.50, is true. You don't have to necessarily write in that statement, but it's a good thing to think about because this is the logic of the hypothesis testing. Our very first step is to assume the truth of the null hypothesis that only 50% of USA adults can correctly identify the correct definition of the Bill of Rights. Assume that's true, we can now say number of successes is going to be equal to n times P naught. That's a pretty fast computation. N is 1,000. P naught is 0.50. So multiply that through, and you get 500 exactly. Which makes sense. We're testing if it's half. So if the null hypothesis is true, half of the sample of 1,000 should be successes. So that's greater than or equal to 10, so it's a pass there. That means number of failures is going to be n minus the number of successes, 500. We're really writing this down just for the sake of the process. Not too bad numbers this time, 1,000 minus 500. But we kind of already knew it's going to be 500 failures as well. This is just a paper trail in the notes more than anything. It's greater than or equal to 10. So we can now say the sample size is large enough. So we have a pass on that condition as well. Now we're ready to just run through the test. We need a test statistic, a p-value, and a good conclusion. Any questions at all, folks, with the condition checking? Okay, for this test statistic portion, part C, what we need to carry down is our p-hat value first. P-hat is 0.459. Okay, so now that we have that value, let's also write, just as an easy reference, the value of P naught we'll need as well. It comes right out of the null hypothesis, but we also state it in context up here. P naught is 0.50. With those two values down, we're ready to just compute the test statistic outright. But it's tricky, so let's take our time once again with this. Best strategy to really get this in your head, even if you have it on your notes for the final exam, the more you write this down, the more your brain just becomes familiar with this formula, the more it becomes more of a process, muscle memory really, and it gets easier to use. Plus, just writing down this formula alone on a final exam setting, that's worth partial credit as well. You told me the right formula. So even if you ran out of time or made mistakes elsewhere, this is a good starting point, even for the sake of partial credit. Okay, so that's what the formula looks like, p hat minus p naught. We in fact know all the numerator values. We wrote them down on the margin over here. The big part of the test statistic is actually the denominator. So next formula to write down, standard deviation of p hat goes square root. Here we need to be careful because this feels like standard error, but it's not. We don't put p hat inside like we did with confidence intervals. We put the hypothesized value inside. P naught, 1 minus P naught, divide by N. Okay, now we can plug in the numbers, fill in the blanks essentially. P naught is 0.50. So 1 minus P naught is 0.50 again. Or if you just went 1 minus 0.50, no harm done, like we did in the last problem. Sample size is 1,000, so that goes in the denominator. And this will give us our value, standard deviation, p hat. So it's second, actually, let me just clear this out. Second power 2 for the root, 0.50 times 0.50. Divide and make sure your square root symbol still extends to cover the denominator of 1,000. And that's our standard deviation for the statistic p hat, assuming the null hypothesis is actually true. Comes out as a 0.015811. Okay, we're nearly there. Now we just plug all that back into the test statistic Z. We'll know how many standard deviations our data is away from the hypothesized value. So 0.459 minus P naught, 0.50, divide the whole thing by 0.015811. So back to the calculator again, we've got 0.459 minus 0.5 divide by, and you can tap these numbers in, but let's do a call out to a really special trick, especially if you type your numbers backwards occasionally like me or just totally wrong. Hit up arrow and enter to paste it down. And now you've got even more accuracy than what we put down on paper. And here is the number of standard deviations. To 4 decimal places, it's negative 2.5931. And you know what? That's a lot of standard deviations. It's, most of the way to 3 standard deviations. That's telling us that if we assume that the null hypothesis, 50% can identify the definition of the Bill of Rights, we assume that's true of all USA adults, well, our data is 2.5, 2.6 standard deviations away from that statement of the null hypothesis. That's really far. The chances of this happening are pretty slim. At a 0.05 significance level, we're probably going to reject this null hypothesis, but the p-value is going to tell us specifically if we will or will not. We don't have to budget or just decide that's enough, or maybe it's on a borderline. We can compute this exactly. So here's the next step, the p-value for the test. First thing to remind ourselves is recall that this was a left-tailed test. Which told us we shade to the left. So throw down your test statistic on the normal curve. Here's that curve one more time. N0, 1. 0 is in the center, but Z, if I count out standard deviations, here's about 1, here's about 2, here's about 3, and Z is right around here. Z equals negative 2.5931. And let me try not to cram that in too badly. Negative 2.5931. We'll shade to the left of that value. So now going down the line of the things we would use, it's normal CDF, where input 1 lower, on a left-tailed test, the lower value is negative 10 power 99, because we're shading to the left without stopping. This is input 2, the upper value. And from those two pieces of information, we've essentially got the p-value. We just need to crank it out. Hit second bars down to normal CDF. Change this to, use a negative key down here, 10 power 99. Flip this one to the test statistic, negative 2.5931. 0.1 is already set, and our test statistic now comes out as pretty small. I mean, it's not using, say, the E there for scientific notation, but that's a lot smaller than most significant levels alphas that you would put down, and ours is a 0.05, so we're way below. Let's record the p-value equals 0.0048 to 2 decimal places. We're going to reject the null hypothesis because this is definitely less than alpha, but it takes time to write down these conclusions really carefully, so I think this is a good stopping point for us. We'll review what we did when we come back tomorrow on Thursday, finalize our conclusion really carefully, then we'll turn it all around and look at hypothesis testing for quantitative data, make an early start on those notes. My goal is to finish that section on Monday or maybe sometime on Wednesday to give us either 2 days or a day and a half full review for the final exam. But we did it, folks. Any last questions before we call it a night? Well, with this stopping point at least. Okay, well, have a great night, everyone. We'll finalize this one up and then get into the last section of the course on tomorrow's class. Drive safe out there. If you're driving, if you're in Zoom, still drive safe if you need to. Yep, have a good one.